Hi, everybody. Thanks for joining today. So I'm John McNally, Principal Academic Solutions Developer here at Wolfram Research. My background is in physics research and education and physics education research. My recent time has been spent talking to a lot of folks about AI and computational pedagogy. I'm one of the industry advisory board members for the American Physical Society group on data science. There's a lot of interest in this in basically any STEM field. How can generative AI be used usefully in education? So without further ado, let's get into it. First of all, what's with the title change? So the talk title has one thing and my slides have another title. So without calling anyone out too much, I think the original title was submitted using a AI summary of a previous talk I had given. That is not a particularly good use of AI for educational purposes. So this could be a teachable moment, again, without calling out anyone too much. But there's some other important reasons why the focus of this talk is a little bit different than just prompting techniques. So for one, there is a trend in folks who are making AI applications that prompting and the reasons why prompting can help should not really be the responsibility of the user. If your user is having to become an expert in such things, you could make the strong argument that maybe something is just wrong with your app. The people that are building these, I think there is a trend toward trying to make that not the problem of the user. So that's one reason. The other reason is that you'll see some examples today of some structural issues that come up with large language models that prompting just simply is not going to fix, and you'll see that as we go. And then the other important point is that tooling can fix things that prompting on their own cannot fix. So this is the reason for the title change. So let's get into the actual agenda today. So I'll talk about sort of a paradigm for how you can think about students developing skills in a context where they are using generative AI, but in a pedagogically useful way, not in a sort of they're not thinking about anything and it's just sort of AI saying whatever it says, right? I'll make the argument that there is actually a way of using these things constructively and show you some examples of that paradigm. Specifically, since these are the audiences that I mostly talk with this about, you'll see an example in chemistry and in physics. And then I'll talk a little bit more generally about things that go into making these sorts of education experiences. So you hear AI agents a lot. So different people can sometimes mean different things when they say this. So I want to clarify some things about AI agents that have come up from various conferences where I've talked about similar topics. So in this presentation, how many AI agents are we talking about here? So the assertion I'm going to make is that you want to really think about AI agents of matching your lesson activity, not is it right for your course? And so what do we even mean by an AI agent? So again, in the language that I'm going to be using today, an AI agent is going to be a language model plus prompting. So prompting is important for agent behavior, but then also the tooling that's around that agent. So if you change any of those things, you have a different AI agent, right? So you could have the exact same prompting and tooling, swap out to a different language model provider. You can think of that as a different AI agent. Likewise, anytime you adjust your prompts when you've got the same language model and tooling, you can think of that as a different AI agent. And again, there are some things that prompting on its own simply doesn't address. And so tooling is an important part of having what we're going to call an AI agent. And so do you mean Wolfram or OpenAI? Maybe at this conference it's less of a obvious question, but so the language model provider, in this case, I'll be using OpenAI, and all of the prompting and tooling came from us here at Wolfram Research. So you can build AI agents out of an amalgam of various resources. So that's an important point to make. So let's get into it. So the paradigm I'm going to suggest for how students can actually use AI and AI agents productively in lesson activities is based off of this sort of progression. So the progression would be coding one, prompting one, building one. Where does that progression come from? There's a paradigm in medical education that surgeons will often use for learning how to become good surgeons. This is a very important job that we want them to be good at what they do because it's really important they get it right, just like it's really important that students have the correct pedagogy in place when they're learning. So there's this concept of graded autonomy where the learner increasingly goes through a less and less scaffolded experience, where at first, you're very much kind of walking them through something step by step. So in the context of surgery, that would be seeing one. In the context of working with the lessons you'll see today, it will be sort of coding, in the sense that coding is often taught where we just sort of see examples and students are parroting back. But then we don't stop there, crucially. So prompting then would be focusing on, okay, let's think about strategic planning of what I want to accomplish to solve a particular problem, and then let automation handle the execution of my plan, right? So the last step then would be thinking about, okay, how can we actually build something that other people can use to solve other problems that are related to the one that I've just studied? So that's the sort of backstory and progression that we'll look at some examples today. And another important thing to keep in mind here is that there's this concept of differentiated instruction, which if you're not an experienced educator like I am, maybe you've heard of, maybe you haven't. So basically the idea behind differentiated instruction is that your course doesn't look the same to every student that is approaching your course. There's various goals that you're going to have, and the way that different cohorts of students attend to those learning goals might look different. So how does this paradigm I've just suggested support differentiated instruction? So when students are going through the process of coding something, in the sense that it's mostly parroting sort of what they're seeing from an expert, that's building procedural and factual knowledge, which there's nothing wrong with. It's in fact the basis for how we're able to make strategic plans and do more advanced things. When we're prompting an AI agent, so this is the part that LLMs really allow us to do something different that we couldn't have done it quite in the same way without them, is that it really emphasizes the strategic planning part, because all of the fine details are being handled by automation. So you go first from building procedural and factual knowledge to focusing on what is the strategic plan here. And that's something that you can engage with by prompting AI agents to execute your plan. Then when we go to, okay, how would one actually think about making such a system like what the student has just interacted with? That gets into systems thinking and even multidisciplinary things like thinking about user experience, all these sorts of things. So the examples that you'll see, I think, really do support differentiated instruction by thinking of this progression of what people are doing with their computation in the classroom. So let's walk through this in this case, chemistry example. So this is the first step, coding one, right? So step one is let's get some lab data. So thanks to Gadaraba from North Carolina State University, whose lab actually took the data that we're looking at today. So step one, the student imports some data. In any language, it's quite easy to do in our language, but in any language, it would be, what are the magic words to import data? Let me type them, right? So again, this, even though we sometimes think of coding as an advanced skill, parts of it are really procedural and factual knowledge, right? So after we've got the data, we could then even hand a student a manipulative, such as this one, that again, if you're looking at the slides and you want to see how any of this is done, there's code, of course, there. But the students might be given something like this, where they're not responsible for building this manipulative yet in that first step, but they can explore and see, okay, how do the kinds of models that we're talking about, so again, defined here, how do they relate to the lab data that we just took? So this step is exploratory, but it's still not really thinking strategically yet. It's just sort of getting a feel for what's going on. So then, of course, we teach the student the magic words that allows them to fit a model, manipulate the data, and get a nicely fit model, and even see what are the % error in this fit of the model. So again, I want to emphasize that even though getting most students to this point of just being able to make something like this, many classrooms would consider that sort of a really like enormous achievement, that your student can just take their lab data and come out with a plot like this. But especially when you're working with a language like Wolfram Language, where the code that goes into this is very high level and allows you to just sort of express what you want to do, we're kind of just teaching what are the magic words to do this process when we go through something like this. So I want to emphasize this is not where we stop. Okay, so what do we do next? How do we bring an AI agent into this? So what your student will probably remember when they leave the classroom might not be any particular combination of magic words, but you want them to remember, okay, what's the plan and point of some various things that I learned, and how can I use them in situations? So let's say that rather than walking the student through how do they write the code for something like this, you can instead have the student come up with the plan for what they want to do. So, okay, let's say I have some data. What do I do with lab data? Well, first I want to get it into a computer. I want to fit it to a particular model. So again, this is the student knowing this and putting this part into the plan where they specify specifically what kind of model they think would be appropriate here. That's where they're bringing in their knowledge. That's student learning, but at a strategic level, not at a details level. So then they know what they want to do is they want to visualize the model next to the observed data. So again, knowing that that's a thing worth doing is knowledge, but not the details level of that knowledge. And then knowing that visualizing percent error and then identifying regions where the percent error is above some threshold, all of that, and knowing like what are thresholds of interest for some particular domain, that's all knowledge worth having and very important knowledge for students to gain, but is independent from the details of how one would implement that, right? So now if a student says something like this and their AI agent has a particular tool, which again has been designed for supporting this specific lesson, not even necessarily an entire course, then the model is able to execute the student's plan of saying, okay, here's the fitted model you wanted, here's the result, here's a nice visualization of the errors and where the thresholds are. And what's more, because there's a specific tool here, if we run this again and wait just a second for the language model to sort of do its thing, the language model will take the student plan, put that into the tooling that it has access to. So again, this tooling is something that has been designed with this particular sequence of instruction in mind. And as the language model churns away here, my internet is fast today. We should get a nice output here any second. I'll stop it if my internet seems to be going too slowly here. Here we are. So still waiting on the language model to finish. Looks like it's almost done. Still typing away. The streaming of the language model is a bit slow today, but you see if you compare this model that it's sort of slowly churning out, that's going to be the same model that it had before, and the pictures will look the same once it gets to that step as well. I'm thinking about stopping this just in the interest of making sure we don't run out of time waiting on the language model. Okay, the joys of, we can at least check that the first coefficient is in fact the same, which indeed it is. So, because it's using the tool, that removes the problem of the language model, having variability in what it does. So, okay, so another thing that we could do is we could also have it make manipulatives, right? So you remember from before, there was the manipulative where, again, the instructor had to make beforehand so that the student can get a sense for what the various parameters in the model actually are. Well, if you give the language model, again, the ability to evaluate tools, or to use tools, excuse me, it can write some Wolfram language code to be able to create a manipulative very similar to the one that was sort of hand created in that initial step of the instruction sequence. So we can also extend it. So again, here, if we say, actually, I want to see not just where the error threshold was what I said before, but let's actually make a more strict error threshold and show me that part. So then the language model is able to, again, use the same specially built tool for this instruction sequence. And we get a plot that then gives you the place to actually learn some chemistry, right? So this empirical model that we have, clearly it's not exactly capturing what's going on. If I go back, this empirical model we see is not quite what's going on in the observed data. And so that's an opportunity to learn, well, okay, so what are some better empirical models or some models based off of chemistry principles that will capture even better what's going on here, even though this is a good model because the error is low compared to what we're seeing. Clearly, when those different steps of the reaction process are happening, there's something that this model is not capturing. And so again, the student is able to get to that point by using an AI agent that has a tool specifically designed to help them get to that point, right? So there's some secret sauce here. So I've linked here what happens if you just try that same thing in a sort of different context, right? So here, this is exactly the same language model. In fact, actually, when I ran this, it's probably even a newer language model in this example that you're seeing here that has the sort of comically thought for 16 seconds and came up with this fit. Sometimes if you run this without giving it the right tool, it can invent the right tool on the fly sometimes, right? But you don't really want that in the context of this instruction sequence. What you actually want is to be able to have the student's plan executed correctly. So that's where having specific tools for a specific instruction sequence in mind is really important. So there is some work in the Journal of Chemical Education that suggested some guidelines for developing custom GPTs. So a custom GPT is, it's basically a sort of AI agent. In this work, they suggested a checklist for folks to keep in mind as they're designing custom GPTs. I'm going to read that as custom agents for use with chemistry instruction. So the checklists there, if we think about, okay, so we want to make sure that we're actually defining the scope and goals of this agent correctly, right? In other words, having this very general purpose thing, like you saw if we just sort of hope for the best with the ChatGPT interface, that's less useful in an educational context than having something which is specifically designed for a specific instructional sequence. So, again, setting those clear expectations. By virtue of the work that we do, the data is safeguarded as much as possible. The system prompt that's being used is something that we've put a lot of work into, again, so that the user doesn't have to worry about that. And then by having access to all of the great tools that you've hopefully seen the talks earlier in this conference about related to retrieval augmented generation, related to using the knowledge base, related to all sorts of nice integrations that you can do where you combine a language model with other sorts of tools, you get a much richer thing than if you just relied on a language model or a language model inventing stuff. Even if it's inventing tools, if you give it a tool is a good tool, that's going to get you a lot more mileage in this context for sure. So then let's talk about the last step in that chain. So we want to extend beyond just prompting, right? So again, we also don't want to stop at just coming up with the strategic plan and then letting automation do the rest. We then want to actually engage with students, have students engage in the idea of, okay, how does one create the kind of automation that allowed that sort of exploration to just happen? And so what you see here is an LLM graph. And again, if you're curious about code for how any of this is made, you can always unfurl. But so this is a pictorial representation of that decomposition fit tool that this particular agent was using. So where differentiated instruction again can come in is a very important thing. For certain classes and certain learning goals, maybe just sketching out a tool like this or sketching out a flow like this is the only thing in the learning goal. I would advocate for a lot of classrooms, what you actually want to do is you actually want to eventually go into the gory details of what actually happens at each of these nodes and knowing the language. But again, it depends on the cohort of students, their age, the class, all sorts of things. But we do want to engage with, okay, how does that automation actually happen? Not just leave it at prompting and then saying, cool, it worked, and that's the end of the lesson, right? So I'm going to very, very briefly go through the illustration physics, just to make sure we have time for Q&A and don't run out of time here. But so this was also inspired by this work on prompt problems, and then again, another case of having very specific tool meant for specific exploration, that if you didn't have that very specific tool, is unlikely to work with the reliability that you would see if you just let a generative model go for it, inventing stuff on the fly. So Denny et al. Back in 2023 suggested prompt problems as a way to assess students' planning and problem-solving abilities in certain domains. Now, in its original formation, the goal was, can you construct a prompt that gets a language model to implement something correctly? There is some interesting pedagogical value in that, because the more that you are able to anticipate possible pitfalls, the more you're able to give more explicit direction. That greatly enhances the chance that the language model will be able to correctly carry out your plan. However, language models without tools are still stochastic. Even with tools, they're the language model part is stochastic, but the tools can be deterministic. So you've got the system where part of it is a bit random, but the tool might be same thing in, same thing out every time. So if the student comes up with a good plan, we don't want them to be penalized by the language model. Just, oh, sorry, I hallucinated this time, and your very good plan didn't work. Not because it wasn't a good plan, just because the language model didn't have what it needed to actually execute the plan. So this is why I think prompt problems are something people in education should be aware of, but I think not maybe the optimal design for how we actually want to use these things mostly. So here's a different sort of system. So before we're like talking about bringing experimental lab data and fitting that to a model. Here we're doing an exploration of like a simple pendulum, where we're looking at what's the difference between approximating or not approximating with small angles. So here the student would come up with some plan, and because the language model has access to a documentation lookup tool and has access to a language evaluator, it is able to come up with this good student plan. So this would be an example of sort of a traditional prompt problem supplemented with lookup and code evaluation. So good, that's better than just a sort of a raw prompt problem, but we can actually do even better than that. So some fraction of the time, if you ask the language model to do this, it might still make a mistake, right? And that's because you're asking it to write the code. If what instead you do is you give the language model a tool that says, okay, give me the inputs to what the plan is, and then which in this case, all the parameters are specified here, the language model can correctly put the inputs into the tool in the right places, and then you deterministically are able to get these sorts of outputs. So if we cut to the punchline of what sort of exploration that tool allows, it's exploring what happens if I adjust various parameters of my physical system, and I see that actually the effects of either approximating versus not approximating that physical system in various ways are different based off of a lot of parameters in the physical system. And so then that's the opportunity to learn a bunch of physics. And that is supported by having a specific tool in a way that sometimes will work if you try to implement it without that specific tool in a language model. But because the language models, and I'll make the point in this slide, are stochastic, you always have to bear that in mind, right? So why not just prompt your way to success every time? So I'll show an example here in an older model and then a newer model. So let's say that you're trying to prompt your way. In this case, GPT-2 is much worse at arithmetic than newer models. But you say, great, I have realized that if I tell GPT-2 it's some sort of expert AI assistant or developer, as opposed to not telling it that, I increase my success probability for it generating the token that I'm hoping it will generate in this situation. That's basically what all prompting boils down to. This is a simplified example because it uses an older model, but any prompting strategy basically boils down to hoping that this chart doesn't look ridiculous. And as you can see, oh, look, there was a ridiculous part of the chart. It turns out that telling it it's a tuba player makes it better at arithmetic than if you had this. But even in something which is conceptually very similar, you swap out, the specific characters for something else, it greatly affects your prompting strategy. Now, again, this is an older model, so you might think, oh, newer models have fixed this. Well, this particular graph doesn't look that ridiculous with newer models, but the point is that any prompting-based strategy, you can always come up with some graph that looks a bit ridiculous like this. And so for a newer model, if you're familiar with trolley problems, where the model has to decide, what to do in some situation where there's a trolley and some stuff on either end, and you don't really want it to crash to either one, but the model has to make up its mind. This was inspired by a nice Anthropic paper recently. This is GPT 4.1, so this is advertised as a frontier model as of today, and you could find people that would have perhaps a sort of similar ethical bent as what the model seems to have picked up in some regime of what you might adjust. But, sort of as a reminder that, there aren't first principles going on in when a language model is making these sorts of completions of text. It's got some weights and some biases from its training data, and then it's using those to compute what's likely to come next. That's the language model part of these AI systems. And so if you put the language model part of these AI systems into certain kinds of situations, you're going to get some ridiculous looking graph where suddenly its opinion on some ethical question radically changes just because it involved 42 versus 43 in that's the only thing changing as part of the prompting situation here, right? So again, the point is not any particular ridiculous looking graph like this. That's just baked into what language models do and how they work. So anytime you have a language model, you're going to be able to come up with some ridiculous graph that prompting is not going to be able to get you out of. So the solution for that is, of course, tools. So the toolkit that we have available to us includes things like semantic search. So another good practice that I won't have time to talk about, but feel free to ask questions and hear about in other places of the conference, is that you should really think about when you have a semantic search index. Why are certain things coming up as being relevant? So here we have an index which was made based off of all of the excellent like fast start to chemistry notebooks that are online for folks. And so if someone says, tell me about stoichiometry, and then the chemical reactions notebook comes up first, why is that? Is that a bug? Well, actually, no. It's because in the way that this particular index was created, there's a part in that notebook that talks exactly about stoichiometry in the context of chemical reactions. And so you want to make sure not to only deliver that particular thing that shows up in the tooltip here, because that's actually not a very useful piece of code for the language model to see. Instead, if we deliver the entire notebook as the payload of what the language model would see, that might be a better context. In the slide here, I've got linked a bunch of things for people to design the sorts of tools that I've been talking about, that again, they're made for specific instructional sequences. Tool repositories, prompt repositories. Of course, Wolfram Alpha is a deterministic tool. So, that's why Wolfram Alpha prompting isn't talked about, because it's deterministic. And then, of course, just knowing the language. So as a recap, as I want to make sure we have time for questions as well, you want to make sure that you have the right AI agent for your specific lesson, not for your course. You also want to understand that there's a real trade-off in a lot of what you'll see between the generality and the reliability of when people say they have AI tools. So a lot of that comes down to language models, right? So if you are able to give language models very specific tools, makes them very reliable. But then if those tools don't apply in a particular case, they can't use that tool. So when you're thinking about how to use language models in various contexts, this generality versus reliability trade-off is, I think, the state of current language models and applications that use language models. So as this translates to pedagogy, remember, hand coding to agent prompting to agent building, you can translate to increasingly giving the student more and more complex things that they're dealing with as learning rote skills, then how to do a strategic plan, and then systems thinking, which would include how to execute strategic plans and enable others to execute strategic plans. So if you want to see the specific tools that I used for this demo, they are public objects there that I would encourage you to take a look at. Feel free to ask any questions. And let me check the Q&A and see if we've got anything. So, okay, so we have a couple of things in chat. So can I share the name of the Anthropic paper? Offhand, I don't remember the name, but it's the one about agentic misalignment. So if you search Anthropic agentic misalignment, that's a good paper. I don't remember its exact name though, offhand. So we have another comment that I am bullish on AI. How do you address the issue that AI erodes student critical thinking? So again, I think you really want to, if you stop here, where, okay, I've prompted the thing and it did the task, you're leaving a whole section of critical thinking completely unaddressed, right? So I think that's my answer to that question, is that if your idea of how a student uses AI is that they just prompt it and then it does the thing and hooray, then yes, you are actually leaving a large part of critical thinking off the table. So let's see. So we have another question. So prompt one being a planning step follows Polya's pedagogy from how to solve it, which is foundational in chemistry education. Hence why the step-by-step chemistry results always have a plan step. Oh, okay, that's great. I was actually unaware of that part of Polya's pedagogy. Thanks for pointing that out. So is that the Anthropic paper in the chat? Let me take a look. Yes, that is the Anthropic paper I was talking about in chat. So again, the experiment I did here is not the same as the experiment they were doing. The point that I'm trying to make, so I should say it's loosely inspired by the experiment they were doing. Just the point I was trying to make is that sort of in any important context where you have a chance of the input to the LLM being out of the training data range that you expect it's seen a lot of examples at, and it's gonna just do what it's been trained to do. So I would not anticipate that this sort of trolley problem but adjust n sort of things wound up in its training set a lot. And so you would expect to see some sort of byproduct of some other adjustment to what its weights and biases are that were helpful in some other context. Oops, gradient descent made it be ridiculous in some other context. So like, again, I'm bullish on AI used well, but I think people need to just be aware of this feature of LLMs that, like, there's a nice cottage industry of always being able to come up with ridiculous graphs like this, and it's kind of fun too. But make sure that you're not just prompting. Make sure that you're prompting and tooling up when you're thinking about AI systems. Would be my 2 cents. Well, thanks everyone. I'm pleased to talk with you on this subject, and feel free to reach out to us. Again, I want to emphasize there is a way to use these kinds of systems incorrectly, and I think there is a way to use them correctly, where they've got the right tooling and pedagogical thoughtfulness built around them, so that again, a very good question that I was asked previously when talking with folks about this is, is the LLM really important for the strategic, excuse me, let me go to the slide I mean to. So is the LLM really critical for the strategic planning step? A language model does allow you to do something that I haven't seen any other kind of system do, and that's the planning can be very, very, very loose natural language. So you can do strategic planning in a slightly more constrained way just by using deterministic Wolfram alpha. But again, there's this like generality versus reliability trade-off that I was speaking about before. So, you know, if you want the plans that people are putting in, if you want to have a slightly bigger delta on what a plan that you think should work would be, I think LLMs really allow that to happen in a way that I haven't seen any other tool allow. So, you know, if the rest of this sounds good, but you're skeptical about LLMs still, I do think that they have sort of a unique opportunity here as compared with anything else that I've seen previously. But you know, a lot of what I'm saying, you know, you don't necessarily have to think of AI including language models. A lot of it would apply in a modified way to other sorts of methods as well. Okay, so enjoy the rest of the conference, everyone.